dear students, let's quickly go through one numerical of your balancing of reciprocating masses. So let's read this. The following data relates to a single cylinder reciprocating engine. So uh, carefully just have a look. Single cylinder reciprocating engine. So this is where we have a crank. Okay, uh, this is the crank. This is the connecting rod, and this is the piston. So this is what we have to balance this part. Okay, so here actually the masses of the whole reciprocating part and the revolving part is given. So mass of reciprocating part is 50 kg. So whatever is reciprocating here, okay, to and from motion, it is 50 kg. And mass of revolving part about the crank, this is the crank and this is the crank radius. Okay, so some mass about the crank radius, okay, that is 35 kg, is revolving around a crank, revolving like this. Okay, so 35 kg at crank radius. So crank radius here is not given to you. Okay, then we have we know the omega value is given, omega speed 200, sorry, omega is not given, rpm is given. Okay, and so from here 200 rpm we can find out the omega angular velocity omega. So that is 2 pi n by 60. That is how we find. Then stroke length is 300 mm. Now the thing is, you know, this is the crank, no? From here. So this is the crank, this is the connecting rod, and this is the piston. Okay. So now see, crank rotates in this direction, in this manner. Okay. So you know, you have studied in your IC engine that when the crank, this crank, okay, reaches here, okay, this is the maximum I mean distance the crank can go here. This is called the top dead center. Okay, top dead center. And when the crank, I'll show it here, reaches here, okay, so that means it is rotating. No, this part will go on like this. This part is going in this direction. So this part when it reaches here, okay, this is the top dead center. And when this part reaches here, this is the bottom dead center. Okay, so between top dead center and bottom dead center, the total length is called the stroke of the engine. Right? So we are given with the stroke length 300. Right. So you see, this is the stroke length between top dead center and bottom dead center, and you know this is the crank that rotates here. So the crank, okay, covers this distance plus this distance. That is the total distance between top dead center and bottom dead center is the total. You can say like the crank length plus crank length will give you the stroke length. Okay, so crank length when it is in the at this position is the top dead center, and when crank is here, this is the bottom dead center. So crank length from the center, the radius of the crank obviously, plus the radius of the crank in this direction is the total stroke length. You can say twice the crank length is equal to stroke length. That is how we relate it. Okay, so that will be useful because we are not given with the radius of the crank. Crank radius is not given, but we can find the crank radius by dividing this 300 by 2, because twice the crank radius is equal to stroke length. Okay, so twice crank length is equal to stroke length. So 2 into crank radius equal to stroke length. So crank radius is 300 by 2. That way we can find out. Okay, now 65% of the reciprocating parts and all the revolving parts are to be balanced. Okay, so we have to balance, see, 65% of this way. I told you that we don't balance the entire amount of mass. So here 65%, that is 0.65 multiplied by 50. So here the value of C, small c, is 0.65. Okay, that is why I will say half here. Half means what? Half means 50%. This is 75%. Okay, so in between that we have to take. So here in the question that they have said that you balance 65% of it. This C is 0.65. Now determine what we determine the balancing mass required at a radius of 320 mm. So this is the crank pin. Okay, this is the mass here. Okay, of the entire revolving part. Okay, we have quantified it at this point, and here we have this stroke. Okay, stroke, and this is the reciprocating mass. So entire reciprocating mass is 50 kg given. Entire revolving mass is given as 35 kg, and the crank radius we can find out. So what is the total mass that has to be placed? Okay, that you need to find out. Okay, total mass that to be placed, and the radius at what it is to be placed is given at as 320. So you have to balance, a balancing mass has to be placed at a radius of 320. So what is the value of the balancing mass? That is what is asked. And the second one is the unbalanced force when the crank has turned 45 degrees from top dead center. So you know the value of the force is given by this equation. See, a resultant unbalanced force. So to find out the unbalanced force using this equation. Okay, so angle at 45 degrees is given. So here theta will be 45 degree for this particular question. So let's begin. So you know length of the crank is half of the stroke. That is what I told. Okay, so that means radius of the crank multiplied plus radius of the crank will be the total stroke because of the top dead center at bottom dead center, because the crank is revolving, rotating. No, this is from the IC engine. So the radius of the crank can be found as 150 mm by dividing 300 by 2. Okay, that is the crank radius. Crank radius. So we know that 35 kg is at 150 mm from the crank center. Okay. Now omega is found already, 2 pi n by 60, n is given. Now we know mass to be balanced at crank pin. This is given by this one. See, mass at the crank pin has to be taken as this. Okay, this is what we need to find out. The first question answer. So this is the mass that we need to balance. Another thing is, do we know the value of C? Yes, C is known. Okay, this M is what? Reciprocating mass. Reciprocating mass is known. So this is given in the question. Right? 50 kg, right? C and M, these two are known. MP, you see, mass at crank pin. Do we know it? Yes, yes. In this case also, we know it because mass at crank pin is this. Okay, this is the, I mean, at crank pin means you can say that this is the crank pin, no? So here, this is the mass that is revolving about this. Okay, so we can just simply say that C is the fraction to be balanced, M is the reciprocating mass, okay, reciprocating in this direction, and MP is the rotating mass about crank pin. Okay, we can say that like that. So here, reciprocating mass is given, rotating mass is given, and the fraction is given 65%. So just by finding this, C is equal to 0.65, M is 50, and MP is 35 given. So you get this as 67.5. So this is the mass that has to be placed. This is the crank. It has to be placed here. And what is the radius? Radius is given as 320. 320. So we have found the balancing mass. Okay, that to be placed at a radius of 320. Now we have to find out the unbalanced force. Force. We have found the mass. How do we have to find the force? Okay. So let's find the force using this problem. Okay. Now the radius is given. Mass we have found already. Omega we know. C is known 0.65 and angle is 45 degrees. Just put all the values. Okay. Oh, I'm sorry. Just a moment. This 67.5 is actually the mass at crank pin. This is mass at crank pin. This, after finding out, we have to balance it. Okay, I'm sorry, I missed that step. So let's just tell it in this manner. What we did is, this is the revolving mass we know. This is the reciprocating mass we know. Okay, so this is the way of combination of these two. Reciprocating mass is this. Okay, this is how it is reciprocating. This is rotating. So that by combining on both of them, we get what? We get a mass here. And the combination process is finding out Cm plus Mp. Okay, so C is the fraction of mass that of the reciprocating mass to be balanced plus the mass revolving about the crank pin. So finally, we take a mass, but this mass combines the reciprocating plus rotating, and we have to balance this mass actually. And this mass is at a radius of crank radius. This is what it is told. So this is crank radius 150. No, 150 we have found 150. So at 150, we have placed this combined mass of reciprocating plus rotating. And what we have to do is we have to balance this mass here by placing an opposite mass. Okay, and it is given in the question that this distance is 320. Sorry, 320. at a distance of 320 mm, we have to balance this mass. This mass combines reciprocating plus revolving. Understood? And you have to balance it by placing an opposite mass to this at a distance of 320. Now, in this case, simplifying this, what we have to do is finally, this is a point, this is the mass. Okay, this mass is known, this mass is cm plus mp. Okay, this is the mass at a distance of 150. Okay, and we need to find a mass here at a distance of 320. Okay, so this mass is known, cm plus mp is 67.5. We have found 67.5. Okay, so we need to find out this mass. What is this mass? Okay. How to find? Just the old process. What we did is M1R1 equal to MCRC. So this is the C means the balance one. So MC into RC equal to M1R1. So this is what we did. So M1R1, I mean, since only one mass is there, so we don't write M1 or R1. We have written M and R only because only one mass is there. MR equal to MCRC. This is at the first place of your balancing problem. We have learned this. We have to see this actually, we have omega square in both directions. MR omega square, MCRC omega square, both are there. So omega square gets cancelled out. Okay, that's why these are actually balancing centrifugal forces. We are about to find the forces only. Before that, we need to find out the mass. So here we have balanced the centrifugal forces. Okay, so using this formula now, MR, this mass is known, 67.5 multiplied by the distance 150 equal to MC, which is unknown, multiplied by the distance 320. This is 320, right? 320. So MC into 320 equal to 67.5 into 150. By solving it, we can find out that 31.64 kg of a balancing mass required to be placed at 320 mm distance from the crank. This is how we balance both the reciprocating and rotating masses. Understood? And now we need to find out simply the unbalanced force just at 45 degree, because at 45 degree angle, it has turned 45 degree from top dead center. Whatever angle is given, just put the angle here at theta. Here also at theta. Okay. So everything else is known. So this is the formula, right? Unbalanced force. So root over 1 minus CMR omega square cos theta whole square plus CMR omega square sin theta whole square. So C is 0.65, put the value, 1 minus 0.65, M is 67.5. Now this M is not MC, okay? This is actually what? The mass, one more thing, yeah. This is the mass that is to be balanced, See, by combining both reciprocating and rotating mass, we get the total mass to be balanced is 67.5. This mass here to be balanced means what? Remains unbalanced. Okay, to be balanced means we have not balanced it. This is unbalanced, and that unbalanced force is caused by an unbalanced mass. So this is the unbalanced mass, right? Unbalanced mass, right? So this unbalanced mass is 67.5. That's why we have to write 67.5 instead of writing this 31. This is balanced. This balances 67.5 kg. 31 kg balances 67 kg. Okay, that we have found what is the mass required, but we need to find that unbalanced force. Okay, what force that we need to balance is caused by the unbalanced mass. Are you getting this? That's why this is your unbalanced mass. Okay, don't write 31 here. This will be unbalanced mass. This is the unbalanced mass, 67.5. So it's this one, 67.5. Remains unbalanced. So this omega is known. See, R is given. This is the radius, right? Crank radius. Unbalanced mass is at 60. This we have actually shown it here. 67.5 is at a distance of 150 mm, isn't it? That's why we have converted it to meter. So 0.150 meter. And this is, see, omega we have found 20 point something, 20.94. Okay, we have to place it here, square, cos square. Similarly, this one, R is 1.15, unbalanced mass is 16.5, and omega is here, sine 45 degree. So we have found out by calculating full thing, we have found the unbalanced force is 2317.56. This is the force that we need to balance. Okay, by placing this mass at a distance of 320 mm, we will get an equivalent opposite force to this, so that we can ultimately balance the entire engine. Okay, reciprocating engine. So this is how we balance the reciprocating engines. This is one example. Okay. In the next lecture, we will go to the balancing of locomotives. But before that, let's just tell you, locomotives are actually, we can tell that you have seen the steam engine, right? There we have used that reciprocating portion. This is the best example of showing the reciprocating portion in a steam engine. You have seen the steam engine, you search in Google that you have in an engine, you have one piston, one crank connecting rod there, okay, and it rotates the and all the engine wheels there. Okay, you have seen this type of a connecting rod rotates the wheels. Okay, and what are the unbalance caused at this locomotive? That is what we need to see. Actually, this is for the locomotive is selected in the books because this gives a best example of reciprocating unbalance here. Okay, so there are two type of locomotive, coupled and uncoupled. Please read about this. Coupled locomotives, here what happens, unbalanced masses can be considered as revolving mass, okay, and can be completely balanced. So that means only about some point, whatever unbalanced mass is there, we consider this as revolving mass about some point. This is similar to the balancing of rotating masses that we have learned before this topic. And in uncoupled locomotives, what happens? The number of planes for consideration of unbalanced masses are separate. This is similar to the part where we have learned that several masses are at different planes. Okay, and there it has caused the unbalance. Okay, now see, we will come to these terms: hammer blow and variation of tractive force and swaying couple. These things we will study in the next coming lecture, and we will see their uses in a numerical. Okay.